So we're going to do an example of a banking problem. Let's imagine that you've got $800 and you deposit it in a bank and you get 6.3% interest. Now that might seem like a very high percentage these days, where most bank accounts are running interest rates are lower than 1%. And you want to look at what happens 8 years later. Well, it depends on how often they calculate your interest, and you might have run into a formula in your earlier years, math years, that looks like this. And this is the compound interest formula. So if we say, let's compound interest. Let's pretend we're going to compound this quarterly. So that means that the n is 4 because you're doing it 4 times a year. And then let's calculate what that's going to equal. So it's $800. The interest rate is 0.063, calculated over 4 periods, and it's 4 times 8 because we're in there for 8 years. And if you pick up a calculator and figure that out, you'll get that your final deposit is now worth $1,319.07. Now, what happens if I asked you, what if you continuously compounded it? So it's not discrete in quarterly periods, but continuously. All of a sudden, this now becomes the law of natural growth, because the change in the amount in your bank is proportional to the amount in your bank account, and it's a continuous scenario. So it follows the law of natural growth. And that means we have a solution for that. That's what the one I just derived. So if we've got this situation to begin with, we know the final amount is going to be A0. A0 is called the principal, e to the kt. And k here is, we don't have to calculate it, we're actually told what it is. It's 6.3%. So we've got 800 and it's 0.063. and time is 8. So if we plug that in, we get $1,324.26. So there is a slight difference if you calculate it quarterly or if you calculate it continuously. Not huge, but enough that if you've got really large principals, you make a big difference. And this is actually how banks calculate their interest continuously for the most part.